Recording in progress.
Chalo, cams on everyone. Let's start off. Last thing that we did, we started with loss of motion. We did free body diagrams. Last class, things were not moving. Everything was at rest. So today, things will start moving. Yeah. So before going to that, you're going to find tensions. This is very important because later on, when we do chapters like elasticity, waves, so there are few chapters, right, where the whole chapter is based on one concept, finding tension. So if you can find tension in the rod, the chapter gets over. So there are like one or two chapters like that. So we'll focus on that a bit. So let me start with a simple thing. Let's say we got a rod here. This is fixed to the wall. And let's say you're applying force F. We got a same rod, but this time there are two forces F. Simple question. Find the tension in the rod. Rod, string, doesn't matter. Simple thing, but the idea is important. What do you guys think? Let's start from there. So let's see this. Now, this is something you need to understand. The tension is not external force. So let me ask you this. Let's draw the free body diagram of the first one. If I ask you, draw the free body diagram of this, what will you draw? So if I draw the free body diagram, FBD of question A, look at the free body diagram. So there is a rod. And what are the forces? You're applying one force here, F, and the wall is also pulling you back. And since this is fixed, acceleration is 0. So therefore, F minus F wall is 0. So F wall is equal to F. So if you actually see this thing, right, these are identical cases. There is no difference between them. Whatever the wall is doing, the same thing this guy is doing. If this F is not there, that thing would have gone ahead. So if you see, A and B are identical cases. The only thing, right, by keeping a wall here, you're hiding the force, but there is a force there. Getting it? So both of them have two forces in opposite direction. There is no difference between both the problems. But you know what most people think? अरे यहाँ पे एक force है, यहाँ पे दो force है. No, here also there are two forces. There's a force due to the wall which is equal to F. Are you clear with this? So when people see this, right, they get a feeling like, oh, यहाँ पे double tension होना चाहिए because you're applying to F. Is that clear? So tension is not the external force. If you say external force, you think about it logically. What is the external force? Zero, isn't it? So tension is not external force. So you might ask, like, then what is tension exactly? Think of like this. Let's say if I take you and tie you to two elephants. No, they don't look like elephants, but let's say if I tie you to two elephants and pull them with equal force, huh? Both the elephants are pulling with equal force. So what is the net force? Zero, right? So you should feel comfortable and relaxed because net force is zero. You're getting the problem there? Net force has nothing to do with tension. Tension is something else. Tension is a force generated inside the body in order to oppose that elongation. So don't get confused between net force and tension. Net force can be zero, but tension will be there. So that is the thing. So how do we find tension? This is the form you can use this. So finding tension in a string or a rod. That's it. Just one thing, remember that, because people have that flow, they see the forces, they think, oh, double ho gaya, or they'll see the net force. So whenever someone asks you find the tension here, find the tension there, assume it is cut there. So just divide the part into two pieces at that point. Assume the string is cut at the point where tension is supposed to be calculated, meaning imaginarily. You are just imagining it is cut there. Now, when you cut it here, you get two systems, right? You'll get the left and the right thing. Draw FBD of any one. So that's the main idea there. Whenever you ask something in the middle, you have to cut it there. Without cutting it, you cannot bring that into the picture and then apply F net is equal to M. That's it. Idea is pretty simple. Now look at our question. This is the rod there. You're applying force that you want to find the tension here. Assume I'm cutting here. Now, when you cut this, I get two pieces here. I'll take this piece here. So this is force F and this is tension. This T is the tension due to the left part, acceleration. So we get F minus T is equal to 0. So tension is equal to F. Same thing. Take this guy. You're applying force F. You're applying force F. You want to find tension somewhere here, cut it. Now, when you do this, you get two parts. This will be F and this will be tension. Similarly, on the left part, this will be tension and this will be F. So what is this T here? This T here, remember in a free body diagram, you draw the forces of the other guy on you. You don't draw your own forces. This is the tension force due to left on right. So if I catch you and pull you, the FBD I will draw on you, that will be my force acting on you. And if you draw my FBD, that will be the force of you on me. So this is a, if you keep together, they will cancel out because it is internal to the tension force. Idea is important. Like, you should be very clear with this. People do get confused. So if you're not confused, then it is great. Right, due to the right part on left. Now you take any one, both are at rest because net force is 0. You get F is equal to T. Tension will remain same. Are you clear with this? If you apply F and F, you won't get double. Clear? So somewhere in 1800s, right? US में, I don't know, meaning I read this story, little credible. This the denims that we use, the denims and all things. So these denims, right, are actually used by industrial workers because these pants are really, so they're made of tough material. They don't tear that easily. They're actually used by industrial workers. So for them, it used to be like, what, if the pant is really strong, the sales used to be good. So there is a company called Levi Strauss, right? It is still there, Levi Jeans. So what they did, they took a pant, right? They tied one side here and they brought a horse and they started pulling the pant. So it was a live exhibition. During that time, there were no TVs and Instagram, right? This is how you do advertisement. So this horse was pulling with full force and the pant was intact. They said, see, look at our pants. They're so strong, even a horse can't tear it. People were really impressed and people started buying it. Next time, or next year, you can say, they brought two horses. and both the horses pulled with equal force. Now they said, look at this band. This can withstand two horses ka force. This is a double strength. You're getting it. But you know the catch, right? If you actually know the physics, you'll understand bullshit. Both are same actually. Previously, there was a wall here. Now there are two horses here. But what people see is two horses, isn't it? If two horses are pulling, then it should be strong. Right? So something like that. So that used to be an ad, it seems. I'm not sure. I did search somewhere. Where are you? There. Thought about that horse will come and pull the pant or something. It is just to show like how strong you are. Yeah, this was the flyer kind of thing. Look at the name also. Overall, spring bottom pants, blanket line clothing, every kind. So Levi Strauss, copper, that's something, all that thing. So if you don't know physics, that's how you can play around. Clear with this? Yeah, that's a basic idea there. So let's see some questions on this. So we have two parallel walls here. You tied a rope. This is A, this is B. Let this angle be alpha. Let this angle be beta. C is the lowest point. So A and B are not at the same level. So there is a small gap there. Now what will happen? This string is pulling with TB. This string is pulling with TA. M is the mass of the rope. So these kind of problems, right, are called catenary problems. So that's a word there, really not that important. So M is the mass of the rope. Uh, so a rope is hanging between. So the rope has mass, it's not massless. So that shape which you get, right, it's not a parabola, it's not a circle. You get something called a hyperbolic function. Like we will see that in math later on. So find the tension at ABC. Alpha and beta are given. If you make alpha is equal to beta, that becomes a standard question which has come multiple times before. The rope is at rest. Catenary. Yeah, you can calculate this. You got an answer, you can type here to the chat box. Hmm. हाँ ना उसका सिंप्लीफाई हो जाएगा. Get me in terms of sin and cos. I think you got it. But just open that as cos and sin and see if you can get something good. I think you got it, but exam में options will be in terms of sin and cos. Mm, let's see. Step one, what to do? Last time I told you the steps, right? Follow the process. Uh, this is FBD. We wrote here. Step one, choose a system, draw an FBD. You start with a free body diagram. You don't know what to do, start with a free body diagram. So let's start with the free body diagram. So this is the rope. So what are the forces? This is your tension, TA. This was alpha. This is tension, TB. This was beta. If you look at the components here, this would be TB cos alpha, TB sin alpha. The weight of the rope is mg. Mass is given. So this would this is TA cos beta. Perfect. Two variables, two equations. You will get it. So TA cos, yeah, writing beta, that's alpha. TA cos alpha plus TB cos beta is mg. That's your vertical forces. TA sin alpha is equal to TB sin beta. That's your equation 2. So take TB and substitute there. Then you end up with TA cos alpha. This guy will come. This side will be sin beta cos alpha plus TA sin alpha cos beta by sin beta is equal to mg. You can see the numerator. That is nothing but sin alpha plus beta, isn't it? That is sin A plus B ka formula. That's what I'm saying. So you can get in terms of sin. So this is mg sin beta sin alpha plus beta. There. So when you substitute there, and then TB will be mg sin alpha by sin alpha plus beta. Check. All clear with this. So your options will be like this: sin alpha plus beta ka terms mein rahega. So in case you got in terms of cot or tan, you have to expand it and get it in this form. What did I do exactly? I wrote forces in vertical, forces in horizontal. Isn't that what we are doing in equilibrium so far? Just because you saw a string alpha beta, don't get scared. Follow the process. Clear with this. The second part of it, we need to find the tension at C also. Now, if you want to find tension at C, you have to cut it at C. That is the catch. But interestingly, right, if you observe, forget about C, if you take tension at any point, let's say if you take a tension here, and let's say if this angle is theta, you will notice something. The horizontal component, which is T cos theta, right? So you will notice the horizontal components TA sine alpha is equal to tension sine theta is equal to TB sine beta. So the horizontal component of tension at any point is constant. Tension will change, alpha will change, but the T sine theta component will remain same. It's a good result. Like so, tension into sine theta is constant. That would be a good theoretical thing. Because your mg will always act downward, right? It will not affect anything in the horizontal direction. You want to find at tension C, so cut it at C. So this is C and this is A. The tension will be along the string, so this is TC. This was TA sine alpha, and this was TA cos alpha. So then you're done. So TC is equal to TA sine alpha. And TA is mg sine alpha sine beta by sine alpha plus beta. Yeah, if alpha is equal to beta, both the strings will be at the same level and you're done. All clear with this? Yukti sine theta, right? What did you say, Yukti? Clear, na? Did I do something wrong? Okay. All clear with this. So in a catenary, when you hang a string, the horizontal component of tension will be same everywhere. All clear with this? So let's see another variation of this. This is even better. You took a rope or a chain and you hanged it. This is a rope of mass m, length L. This is theta, this is theta. So it is hanging at rest. Now exactly from here to the lowest point, this height is y. I didn't draw properly, but this is the lowest point. I should a little to the side. Hmm. Find y. So you took a rope of mass and length L and you're hanging. That middle ka part depth is y. So basically it is also called a sag, S-A-G. So it's like a sag in the middle. So yeah. How do we approach this? Think, take a minute or two. Idea is important. It's a good one. We can put a star for this. Think, take a minute or two. What is the shape of the curve? We don't know. It's not a circle. It's not a parabola. It's some hyperbolic function. You can't calculate all. It's pretty messed up. Max, I think when they teach you the integration and stuff, maybe then you can figure it out. It'll be something like e power x plus e power minus x type functions. But we don't need it. I'll help you see. Find the tension here and find the tension here. Start from there. That you can handle it. Get it. You will need those two. Find the tension at this topmost point and the lowest point. Like what we did, that was easy. That would be the raw material you need. After that, we need to think. Found the tensions? So if you take tension T here and tension T here, I'll call it A and I'll call this A and I'll call this B. You can clearly see the total vertical tension to TA sine theta is equal to mg. So from here we get the tension at A is mg by 2 sine theta. Now if you take half of the string, this would be TA sine theta, this would be TA cos theta, and this would be TB. Meaning, if you want to put the weight, we can put the weight also mg by 2 because symmetrical, half of the weight will be there. We don't need it here, but yeah, TA cos theta is equal to TB. So tension at B will be mg by 2 cot theta. There, I know the tension at A, tension at B. Now listen. This is a catch. So when that rope is there hanging, consider a small part of the rope, ds. We are taking a small part of the rope, ds. So if I magnify this, the picture will look like this. Now if you look at the tensions here, this side, the tension will be T plus dt. The tension will increase slightly. The tension will be T. So remember this thing, we always assume the functions are increasing. Since both the sides the tension is different, and because of this rope will also have a weight of small weight dmg. So this is the weight of that small piece ds. And how much will that mass be? Think about it. For a length L, we have mass m. Then for a ds, we have mass dm, unitary method. So dm will be total mass by total length into ds. That is the mass of the small piece. And similarly here, when you're taking this, if you draw a small tangent, let's say this is making an angle theta. Now this thing has become like a small block on an incline, kind of like this. It has become like an incline making an angle theta. Tension. Great. And you know what are the components? So if you try to resolve this mg into components, we get two components here. We are mostly interested in this component. So if you resolve this into components, yeah, it's not exactly straight. Basically, it's a little curved, but yeah, for our assumptions, it works out. T plus dt. This would be tension, and this component will be dmg sine theta. Remember this? The component along the incline is dmg sine theta. There. So from here, if you solve this, we end up with a dt. So T plus dt is tension plus dmg sine theta. And from here we get dt is equal to dmg sine theta. But what is dm? M by L g ds sine theta. But what is ds sine theta? This was your ds. This was your theta. This height is dy. This height is dx. So ds sine theta is dy. So we got dt is equal to mg by L dy. That means the change in tension of that small piece depends only on the vertical height. It actually doesn't depend on the length of the string. Now, if I integrate this on both the sides, dt is equal to mg by L dy. So when you go from 0 to y, so 0 is the lowest point. That is where your point B is there. So the limits will go from tension at B to tension at A. So this would be tension at minus A minus tension at B is equal to mg y by L. And there y is nothing but TA you know, TB you know, into L by mg. That's your y. Quite an important thing. You will again encounter this thing in this chapter only. Again, you'll encounter this in friction. You'll encounter this in multiple places. If you actually see, we really didn't do big integration. The idea was this: since the tension is changing at every small section, I'll take a small piece of ds. I drew an FBD for that ds, so the ds will have a dmg. Uska jo tangential component is there, that is what is creating the tension, extra tension. Think about it. If it was massless, this will be tension, this will be tension, right? The reason you got that extra tension is because of dmg sine theta. This component will not affect the tension. But interestingly, we got ds sine theta became dy. So it actually depends only on the vertical height and not the actual length of the rope. How do you know the angle is equal to the rope? No, it's actually not theta. It was my mistake. Uh, कुछ और angle ले लेना. I just wanted some angle there. It's not the same angle. This is some phi. It would cancel off anyway. We never needed it. I forgot we already have theta. This is phi. That is phi. Yeah, that is phi. That's not theta. That is some random angle which is changing. All clear with this. So we can general. And did you observe one more thing? This didn't care about the shape of the string also. This does not matter what is the shape of the string. So we can generalize a result. It's a good result. So if you have some rope hanging at any point, if you say this is point A and if you say this is point B, right? And this height is Y, or let's say I'll just take it like this. So let's say this is your origin. Let's say this is YB and this is YA. So the difference in tensions, TA minus TB, will be simply M, the total mass of the rope, M by L into G into YA minus YB. The difference in height. Independent of shape of the string. Is that clear, everyone? Clear with the idea there? So this is a general result. It doesn't matter like what shape you take, you can do this. It only depends on that height between the 2 points. Total mass and total length तो देना पड़ेगा उनको. All clear with this result. So let's play around with this a bit more then. So then this can be extended to a problem like this. So let's say we have a sphere. This is a fixed sphere. Fixed smooth cylinder. Someone took a rope. This is theta. This is a rope of mass m. The radius is r. Now tell me, if I keep a rope like this on a smooth surface, will it stay there? It will fall down. So what you did, you took a light string and you tied it to the wall to keep it at rest. This is a light string. So this string, the red one, didn't have mass. Find tension. So if you cut that string, this black thing will just slide and fall down. Sometimes, right, instead of mass, they will give you something called linear density. ठीक है. Any answers? I thought you guys will just tell it. Let me tell you like this. For simplicity, forget about the damn cylinder. It is not there. Now, doesn't this look like the previous question? What is the tension here? Will there be any tension there? Is it pulling anyone there? No. So tension will be zero. So this tension minus this tension will be this difference in height, isn't it? Mg by L into that height. You're done. But still, if you feel like, no, sir, this is not looking like the previous one, let's prove it. Let me prove it for even more hopeless situation. Let's say we have an incline like this. This is even better. Now let's say there is a rope here. So you have some weird random curved surface. And let's say this is smooth. This height is h and this base is L. And let's say this is tied by a string T1, and let's say this is tied by a string T2, something like this. So this whole string is tight. Just a thing. So how do we do? Same story. We will say consider a small piece here ds. So when you take this small piece ds, now see here everywhere theta is changing. Same story. Here the tension will be T plus gt. Here the tension will be T. This will be your small weight dmg. This will give you a component in this direction, dmg sine theta. So if this was ds, this was theta. then we can clearly see dt is nothing but dmg sine theta. This is nothing but total mass by total length into ds, that is your dm. So we get dt is equal to mg by L ds sine theta. Nothing changed if you say exactly same equation. So tension mg by L into d, because this would be dy, this would be dx. If you integrate this on both sides, so when the height goes from 0 to y, and when the y coordinate is 0, tension is T2 and this is T1. It doesn't matter with the shape of the string. Mg by L into y. Same formula, nothing changes. Is that making sense? Now coming back to our question. So basically you can use it for anything. Now you can make your life a little easy and faster here. So when you take this curved rope, this is one more important point. Free ends will always have zero tension, quite an important thing. This is called a free end. Free end meaning it is not connected to anything. It is not attached to anything. So free ends, so this is a free end, will have zero tension. Because remember, how do we find tension? We cut it here, isn't it? When you cut it there, is there anything on the right? No. So will it pull anything? No. So that's no tension there. How did I get mg by L? Uh, Forgot unitary method here. If the total length L has mass m, then small length ds will have small mass dm. Right, Karthik? Meaning m is the total mass of the rope. This cell and this cell are not same. I hope that's what is confusing you, okay? Both are not same L. M is the mass of the rope and small L is the length of the rope, the entire curved path. Yeah, there is a name for this thing. M by L is called linear density. We will define it later on. But Karthik, clear with this? Then, so free ends have zero tension. So because there's nothing to pull there, so that means at this point, tension is zero. Then the only guy left is this part of the tension. So you just wanted the height between them. So how much is this from geometry? This will be r cos theta. So this height will be r into 1 minus cos theta. There, apply the formula. So tension, this is 0 is equal to total mass is m. G by length of the rope here is r theta, arc length into height y. So this will be mg by r theta into r into 1 minus cos theta. R gets cancelled. We end up with mg by theta in radians and 1 minus cos theta. Is that clear, everyone? How do we solve this? Meaning the same way you will solve. You will take a small ds and you'll play this game every time. I showed you for a random amoeba rope. So if it is valid for this, it's valid for any shape. Is this clear, everyone? That's a good technique. Like, so basically when you're hanging anything or something is lying on an incline also, you have to be careful. This has to be smooth. If it is rough, there will be a friction. If there is a friction, then there'll be one more force tangentially. We are not going to deal with it right now. So that's one thing you have to be careful. All clear with this? We will see that in friction anyway. So there. So all this thing, if you see, right, they'll come under one category there. Great. Let's go ahead. Let's do something a little simpler one. We got an incline, theta. This is height h. This is a fixed smooth incline. You took a block at the top of mass m and released it from rest. Find the time taken to reach the ground. Same question. So this is a 3.5 turns helix. The radius is r and the height is h. So you kept a ring here. So this is point A and this is B. So this is a ring which slides on the helix. So this will slide and finally come down to B. Same thing. Find the time taken to reach the ground. Solution, this one. Yeah. This was a formula, right? T1 minus T2 is mg by L into y. Let's get this. These two questions are exactly same questions. This is one thing you guys need to learn. Like when you see a question, don't think like everything is new. You need to ask yourself, does this look like something which I already know? And most of the time, 80% of the time, the answer is yes. We are not doing any PhD or rocket science here. Even if it is an advanced paper, you will see some questions which are quite similar to something you have done before. That itself will give you speed and put you at an advantage. So let's see. The first was easy. I don't remember the answer, Yukti. Could be right. I'll show you. Get the second part. Yeah, I think that might be the answer. I know. Exam, you'll see the second one. But if you realize it's the same as the first one, it is over. And I hope you guys remember what is a helix. We did study helix. In case you forgot, if you see an helix and get scared, that means you don't remember what is an helix. Helix we saw in kinematics. Here, question number 2. Yeah, 4.5 turns. I gave 3.5 turns. A and B, they look same. And I told you this thing. What is a helix? If you remember, this was a story. We had a full discussion on a helix. If you take a rectangle and draw a diagonal, and if you fold the rectangle into a cylinder, the shape, the curve you get is a helix. That this was the thing. So basically, when you open the helix, it becomes like a diagonal for a rectangle. Means it becomes an incline, isn't it? The ring will think it is like an incline. That was the idea. You have to convert the helix. So this is page 10, kinematics. I'll put there. You should refer this in case you forgot about a helix. This is what I am saying. Every time we'll keep going back. Now I have vectors, calculus, and kinematics, 3 chapters to go back. Imagine when you're doing 15 chapter. That connection is important. Let's see the first one. So we have an incline. This is your height h. This is your theta. Step 1, draw your free body diagram. The thing will never change. The idea is always the same. So if you draw the forces on the block, we have normal reaction. By now, remember this, the component, this will be mg sine theta. This will be mg cos theta. Step 2, assign your accelerations. It will go in this direction. It cannot go up and down because the incline won't let you go. Perfect. So in this direction, we have mg sine theta. That is the only force acting in that direction is equal to mass into acceleration. We are using F is equal to ma. So acceleration is g sine theta. So if you put a block on an incline, it is simply going to slide with an acceleration of g sine theta. Once you got the acceleration, then we have to use kinematics. So whole this length here is h by sine theta. Initially, your velocity is 0 starting from rest. We are using the equation s is equal to ut plus half at square because acceleration is constant. So s is h by sine theta. Acceleration is g sine theta. And that will be a time square. And that would be root 2h by g sine square theta. That was easy, right? Now, how do you convert this into the helix? So an helix is as good as basically if you take a rectangle of same height. So this was point A and this is point B. So this is point A and this is point B. And if you make a rectangle here and if you just stretch it, there, this is how it would be. This is height h. You said this is 3.5 turns. So this base will be, so one turn will give you one circumference. 3.5 turns will give you 3.52 pi r. 7 pi r. That was the idea there. This angle will be theta. And now you kept a ring on this guy here. So basically the ring will simply slide on this. It has become an inclined question. This ring will slide down with g sine theta. Tan theta will be h by 7 pi r. Now, from the previous question, it looks like part A. So the time taken will be root over 2h by g sine square theta. So from tan theta, I hope you remember how to get sine theta, make a triangle. This would be h. 2 pi r root over h square plus 4 pi square r square. So get sine theta from here and substitute. Yeah, it looks big, but it's not a tough question. The main thing was to figuring out that the helix is same as an incline. Once you got this question is as good as the previous one. The motion on a helix, motion along a helix is the same as the motion along an incline. All clear with this? There. So question, the only thing is about the helix, you have to be careful. Let's see one more. This is M, 2M, 3M, 4M, and 5M. There are 5 blocks. Someone is pushing here with 2F, someone here pushing here with force F. All surfaces are smooth. Find acceleration. And normal reaction between M and 2M. So M and 2M will be pushing each other. What is that normal reaction? 2m and 3m. There, let's get this. Yeah, acceleration is easy. Let's get that. Yeah, acceleration is easy. Get me the normal reaction. F5. Okay. Could be right. Another 30, 40 seconds. How to do this? Always keep this in mind. Someone asks you, find the tension there, find the tension in the middle, find the tension at that point. Indirectly is telling you, boss, cut it there. Assume an imaginary cutting there, then you'll get two pieces. Draw an FBD for each piece separately. Take any one and solve. Idea is always the same. Any chapter, anywhere, someone asks you what is there happening in the middle of the problem. You have to cut it there. Without cutting, you won't get that piece. So let's see. Step one, choose your system. I will choose all as my system. Step two, assign acceleration. So I will assign my acceleration. So my system is all the blocks. So net force 2F minus F is the total mass, which is 15m into acceleration. Right? Right. Remember, be careful. Huh? This is acceleration curve terms. These are force curve terms. Don't mix it up. So from there, we get acceleration is F by 15m. Perfect. Next thing, you want to find the tension between m and 2m. So cut it here. Choose any one piece. I'll show you both. Like you can take any one. I'll just show you how it looks if I take any of them. So if I take the left part, the free body diagram will look like this. 5m, 4m, and 3m. Now, if you look at the forces, this will be 2f. Let this thing call it as n23, and this is the acceleration. So for these three blocks, right, they don't know who is m and who is 2m and who is f. They don't know who are those. They will think the force is n23. So 2f minus n23 is, how much is this thing? 549, 12 ma. So n23 is 2f minus 12 ma. That is 12f by 15. That's 3, 4, 4 by 5, 10 minus 6, 30, that, yeah, 6f by 5. If you say, sir, what about the other part? You can do that. Nothing wrong if you take the other part. So it is taken care of. The moment you got acceleration, it is taken care of F. But remember, this time N23 will push this way. It will always push, the normal reaction is pushing away. This is your acceleration. Now, when you write the equation, you'll write N23 minus F is equal to 3m into acceleration. Yes, 6f by 5. It doesn't matter which part you take, it should give you the same answer. All clear with this? Idea is clear how you are approaching this? So how you choose your system? It depends. You want tension in the middle, cut it there. You want normalization in the middle, cut it there. Simple. You want something in the middle, you cut it there. Without cutting, you're not going to get it. Because if you don't cut it, this N23 and this N23 will be always become an internal force. They'll always cancel out. So you cannot extract it, from there. You have to cut it. Clear? Take a break. Come back by 9:40. We'll continue from here. We'll do more. Chalo, camps on everyone. There we have two blocks, 3 kg block and a 5 kg block connected by a 2 kg rope. This whole setup is pulled up with 200 newtons of force. So find the acceleration of the system and find the tension at A, B, and C. So A is the topmost point of the rope, B is the midpoint, and C is the lower part of the rope. Yeah, easy one. Another like mains cards, an easy question. They do ask you questions like this. Let's get this. Yeah, like I said, things are moving, so we will move them slowly and then they'll move them deadly. Others do keep your cams on. So finding tension at a point is a very important thing. Comes a lot. There is this chapter, elasticity. Literally, the whole chapter is finding tension. Other scams on. Any answers? Okay, let's see. The accession part was the easy part. Yukti, just look at your answers. What is the force that I'm applying? 200. How did you generate more than that? So if you can generate more force than what I give you with like this thing, you are the pioneer of humanity. Like we need people like you to take human to, next level of advancement and civilization. So that's what I keep telling you. It is okay to get wrong answers, but when you get blunders, you should realize that you forgot MG. So let's see. So step one, take your whole system. I'll take the whole thing as my system. See, when you say system, you can take anything as a system. So my system is this whole thing. So I'll just treat this as one big block. Then the total weight will be 100 newtons, and this will be your acceleration. And that was a mistake, I guess. So now when you write the forces, F minus 100 is equal to 10 into A. So this is 200. So there we get acceleration is 10 meter per second square. Perfect. What do you want to find? Tension at A, cut it at A. So cut here. If you cut it, I'll get an upper part and a lower part. I will take the upper part. Now, how do you know which one to take? Yeah, you can take anything, but always prefer to take which is smaller and simpler, right? If you take the upper part, there's only one block. Why you want to deal with rope and everything? Now, what are the forces? 200 at your own weight, 13 newtons. And the string is always pulling, tension at TA. And don't forget you're accelerating. Now, keep this thing in mind. This is how I draw. Keep all the forces on the body and keep the accelerations outside the body. Clear them. Keep it clear. Keep your picture clear. You might get the answers, but later on, as things become more complex, you will mess up. So keep the forces on the body and keep the acceleration outside. Now write it down. Net force 200. Up is positive, down is negative. Keep your convention simple. TA is equal to mass of the body into acceleration. So that's 140. Then what do you want to find? B, cut it here. You want to find, cut it, as simple as that. So when you cut it, you can take anything you want. I will again take the upper part. This is how it will look. This is 200. Now your total weight will be, now remember B is the midpoint. So this was 1 kg and this was 1 kg. So this whole setup is acting like a 4 kg block. So this was 14 Newton. So this whole setup is like 4 kg block. And the tension would be TB. Acceleration, same story. So this would be 200 minus 40 minus TB is equal to 4 into acceleration 10. So we get TB is equal to 120. Great. You want to tension at C? I will take only the 5 kg block. This would be TC, your own weight, 50, and yeah, you're done. Acceleration. So TC minus 50 is equal to 5 into 10. So TC is 100 newtons. Check. Is it all clear, everyone? Draw your FBD, put your forces, put your accelerations, write net force is equal to mass into acceleration. That's, keep it simple. And always put a picture. Don't be lazy to draw a picture. The more pictures you draw while practicing, examing, you can actually skip pictures. But if you make it a habit during learning, the exam, you will not be able to do it. If you see every equation and draw a picture, just put a small damn picture. That's it. It really helps you a lot. The reason is simple. When you put it on a paper and you put a picture, right, you're teaching your brain how to visualize in air. It helps a lot. If I'm doing it in the exam, I will not be drawing this many pictures. I will see and get the answers also sometimes. That will come only when you do things first systematically. Next thing. This would be an important question, and this would come again and again. So instead of blocks, what if you have a rope? Again, not a tough one, but the idea is important. So we have a rope on a smooth floor. This is a uniform rope of mass m and length L. So this point is x is equal to 0, and this point is x is equal to L. So x is, that is the thing there. So let's say you're applying force F here. You're applying force to F and you're applying force F. This distance is x. So find the tension at a distance x from the right end. So if you pull a rope with a force F, the tension varies. Everywhere the tension won't be same. So what is the tension at a distance x from the right end? You actually don't need this x is equal to 0 and L thing. They will simply say find tension as function of x coordinate, but yeah. Find tension at a distance x from right end. Standard model. Remember this. Useful. Meaning, don't remember the result. Remember how we do it. Finish off. It's an easy one. And look at the thing. Huh? They have same net force. Net force is same. Right, Ahna. Nee, Rohit. Think about what you got. If you put x is equal to 0, you're getting infinity. Right, Karthik? Meaning, I'll tell you one thing, see. If it's the CET thing, you can actually guess. If I put x is equal to 0, where are you? You're on the right end. So what should be the tension? F. So in the options, if you put x0, you should get F. If you put x is equal to well, you're on the free end. What's the tension? 0. If you put x is equal to 0, what's the tension? 2F. If you put x is equal to what's the tension? F. So you can actually eliminate options. Yeah, मेंस में एडवांस में नहीं होगा, but सीईटी में तो you can definitely guess. They give sometimes really super dumb options. I told you, right? There was some question root over some 2x square minus x plus 1, blah, blah, blah. Almost 6, 7, half page ka question that was almost not one fourth of the page. And that was like find mod x. That was the question. And options are -1, -2, -3, and 1. That was the question. I was like, what? I think I wasted time getting surprised by the options and actually solving the question. But anyway, so how to do? Step one, choose your system. The whole thing is my system. Great. Then get the acceleration. Net force is equal to mass into acceleration. I'll always draw a bracket like that because I have seen what people do. They write ma and they do f. Plus ma is equal to 0. Then they get confused. Minus kaha pe? Matlab, they think ma is a force. So be careful with that. At least for a few days I will write it, but later on I'll skip it. So acceleration is f by m. You want to find tension there? Cut it there. If you cut it there, then I can take a left or the right part. I will take the right part. So this is the catch in the question. When you take the right part, don't forget the mass also changed. Now this guy ka mass will be small m. How can the mass remain same if you cut it? So this is F, this is tension, and this is acceleration. Since it is a uniform mass, I can use unitary method. For length L, mass is capital M. For length X, the mass is small m. So small m will be m by L into X. Total mass by total length into the X part. So we get F minus T is equal to small m into acceleration. That is the whole catch. The mass changes. So that would be mx by L and acceleration is F by m. So we get tension is F into 1 minus x by L. So in case you're struggling, that was a catch in the question. The piece which you're cutting, mass will be different. You could have taken the left part, the mass would be different. Same story here. Acceleration, I get the same thing, F is equal to ma. When you take the right part, this will be 2f and this will be t and this will be acceleration. This is m. 2f minus t is equal to ma. So m by L, f by m by Lex f into 2 minus x by L. So even though the net force is same, the tension does change. All clear with this? Clear? Good questions. So later on, they'll ask you, find the elongation in the rod. If you apply force, the rod will stretch. So how much did it stretch? That would be a good question. Great. Now let's go ahead a little more. We got a block here of mass 2m. This is connected to a pulley. Mass m, and this is theta. Smooth. Find the acceleration of the blocks at this instant. Initially, blocks are at rest. So you're holding them. Find the acceleration of the blocks at the instant when they're released. What to do? Remember the process. Step 1, choose your system, draw an FPD. Assign accelerations to the bodies. Find relation between them. Choose your X and Y axis, resolve the forces and accelerations. Apply F is equal to ma and solve. That's it. Let me give you anything. That's the process. Just because the problem looks different doesn't mean the process will change. Try. You got 2-3 minutes. Can the block fly off? Think about it. Can the block really fly off? I made sure. What is the mass of the block? 2m. What is the mass of the other block? So can m lift 2m? One more minute and then I'll show you. You continue doing though, because by the time I write equations and all, you get another minute. So let's see whether you got the equations right. If you got the equations, then it is all math. So that is okay. Okay, let's see. Step 1, draw the free body diagrams. No, Rohit, that's not the answer. So this is 2m, this is m. So this is tension. This is normal reaction. This is 2 mg, which we don't need, but he can. And this is theta. These are all the forces. This is tension. This is mg. These are all the forces. Step 2, assign accelerations. Let this go with a1. Let this go with a2. Most common mistake I have seen people doing. For some reason, they think this block is at rest, and they take t is equal to mg. They take t is equal to mg. Sometimes it happens. So this is step 2. And find the relation between the accelerations. So how do you find the relation between accelerations? We use the power method, the method 2. But be careful. You cannot use the power method T1 V1 when theta is changing. So we have to do it for velocities V1 and V2. Power method works for velocities. And if theta is constant, it would have worked for accelerations also. So this will be minus t v1 plus v2 cos theta is equal to 0. So we get v1 is equal to v2 cos theta. Differentiate on both sides. Now, this is important. If you have not done this right, luckily you would still get the answer. And you will see why. dv1 by dt is equal to dv2 dt cos theta plus v2 cos theta का differential is minus sin theta d theta by dt. Now, luckily, we said initially the blocks are at rest. And because of that one reason, this term becomes 0. And you got saved. You get a1 is equal to a2 cos theta. So it would have worked. But if initially the block had some velocity, you would have been gone. Like if they said the initial velocity of the block was u, yeah, then it really won't be that great. But there, we got the relation. You're done. Write the forces horizontal, vertical. Vertical, I don't care because it's only moving horizontally. T cos theta is equal to 2m into acceleration. For this guy, it is tension minus mg is equal to mass into acceleration. I'm taking up positive, down negative. You can do it. 3 equations, 3 variables. Check your equations. If you got these equations, you're done. You got it. Now it is just a matter of solving. Let's dump everything in one place. Take this guy, dump it here. Take this guy, dump it here. So this will be 2m a2 by cos theta minus mg minus ma2 cos theta. Take out a2 common. Capital M will cancel. We'll end up with g cos theta by cos square theta plus 2. I think that's the answer. Yeah, once you got a2, you'll get a1 from there and you're done. Check your steps. See where it went wrong. I followed the process. FBD, SI and accelerations. You see, if 3 different bodies put A1, A2, A3, don't assume anything until unless you're sure. Then use constraints, find the relation. Always check, is theta changing or not changing? Not changing, then fine. Changing, then this is how you do. You do it for velocities and then differentiate. But luckily, it would have worked here for you. All clear with the equations? Yeah, that is okay. है ना? मतलब, you can see the main thing is the getting the equations. How you solve is just up to you, right? Whichever is convenient for you. All got this? Let's see one more. Now, this is a more standard model. So we have a pulley here, M1 and M2. This is also called as an Atwood machine. Yeah, not difficult thing, but do remember the result. Useful, saves you time, comes a lot of places. Find tension in the string and the acceleration of the blocks. Which one is bigger doesn't matter. Assume anyone is bigger. The science will take care of it. That's one good thing in NLM. Let's get this. If velocity was not theta, initially I need more information. I need this height. Then yeah, the equation mein. Then we can say sine tan theta is h by x. Then you differentiate tan theta. From there you get d theta by dt. And dx by dt will be velocity of this guy. Meaning if you see this question, right, you will see it gives you this question ka vibes, isn't it? Just rotate the page 180 degrees. It kind of looks like that. So you need that extra information. You need that height. Only then you can solve, or else we can't. Let's see. Yeah, this is a standard thing. Nee, Rohit, it does depend on the masses, right? How can you get without masses? So let's see. Step one, choose your body, draw the FBD, find the accelerations. Luckily, we know both will have same accelerations in the opposite direction. So tension T, this is M1G, this is tension, and this is M2G, the same string. So if you take, I'll take M2 is greater. So if I take this is going down and this will go up. Write your equation. So T minus M1G is M1 into acceleration. The second Gaussian equation will be T minus M2G is equal to M2 into minus A. Right? See, you can take even down as positive and do it. But I'm telling you, when you're learning in the beginning, try to keep things as, repetitive as possible. And once you get used to it, then you can break it. So it's always like that. Up positive, down negative. That's what we are doing from kinematics. But if it is me in the exam, I won't write like that. I'll write M2G minus T is equal to MA. Up to you. Solve these two equations. You will get acceleration will be M2 minus M1 by M2 plus M. If you have taken M1 is greater, you'll get M1 minus M2G. Tension will be 2 M1 M2 by M1 plus M2G. You can solve that, but remember this. Useful results saves you time. They come a lot. If M2 is greater than M1, you'll get positive. Means your assumption was right. If M2 is less than M1, you'll get a negative sign. Sign will take care of it. All clear with this? Now, there is a way to do this without writing so many equations. And listen to this. This is important because the same thing I'll teach you again in rotational mechanics. I call this thing net force method. And I just named it something. It will be easy to recall. The idea was this. Since if I want acceleration, since anyway tension is getting cancelled, so this is my idea there. M1, M2, just look at the forces acting there. So what I'm suggesting, right? Let's make this straight. Meaning, if I draw like this, meaning I'll just make it flat. Now look at the forces. Now this gives you a feeling as if M2G is pulling here, M1G is pulling back, acceleration, acceleration. So that A, instead of saying A is going up and down, I will say A is the acceleration along the string. Is that making sense? So basically, I'm treating my x-axis as a curve. Making sense? Because see, Max doesn't care as long as the equations look same. Now look at this thing. What is the net force? M2G minus M1G is equal to total mass, M1 plus M2. Acceleration, both are same. Acceleration is equal to M2 minus M1 by M2 plus M1. One step. So this is how you can write. So acceleration will be net force along the string. So along the string, that is the word. We are not taking up and down, we are taking forces along the string by total mass. The only problem with this will work only when all the blocks have same magnitude of acceleration. If they have different accelerations, it doesn't work. So simple, neat trick. Basically, we are just eliminating tension from there and we're writing. But so this is valid only if the blocks have same magnitude of acceleration. They can have different direction. Magnitude should be same. So in certain cases, right, this will actually save you a lot of time. So let me show you a few more on this. Now you guys try using this method. So let's say this is 2M, this is a block. It need not be always an Atwood machine, it can be anything. And you will see this method really shines when you have a lot of blocks. All surfaces are smooth. Find the acceleration of the blocks. Without writing those equations. You're going to use the net force method. Why did you writing? Why are you writing? Listen. You are supposed to take the forces along the string. Look at this thing. So this is the string. What is M1 doing? It's pulling along the string, M2 along the string. So ask yourself, is M2 supporting acceleration or opposing acceleration? Supporting, right? So plus M2G. Look at this M1G. Is it supporting or opposing acceleration? Opposing, right? So minus M1G. So net force is M2G minus M1G, total mass acceleration. That's the idea there. So let me show you this. So first thing, just write the forces. See, this is your string, okay? You should take forces along the string. So this is your mg. For 2 mg, there is no force. There is no force along the string. So yeah, there is a weight 2 mg, but there is no force along the string. Perfect. So this is the acceleration. This is the acceleration. So acceleration is a net force along the string. You can define A in any direction. Now, next thing you need to ask yourself, see, more intuitive thing, that mg, is it supporting acceleration or opposing acceleration? It is supporting. Is 2 mg, is there any component of 2 mg? No, 2 mg is doing nothing. So you're done. The total mass is 2m plus m, g by 3. Is that making sense? Is that logic making sense? The only force to pull the system is mg. The 2 mg guy is doing nothing. Same logic here. What is this component? m1g sine theta 1. What is this component? m2g sine theta 2. I don't know which way it will go. I'll assume it is going this way. A, so then it has to go upward. Same question, ask yourself. M1g sine theta 1 is doing what? It is helping the acceleration, same direction. What is M2g sine? It is opposing you, M2g sine theta 2. So both are fighting by total mass. The net force by total mass. Done. You got an answer. Is that making sense, everyone? Ananya, clear with that? Rohit, Shlok, Shriya? Now, this method will really shine when you have a lot of blocks like this. You have blocks like this, 6 blocks. Let this angle be alpha, let this angle be beta. Let this string ka tension be T. Find the acceleration of the blocks and the tension T in that string. If you try to do it normally, we have to draw 6 FBDs, 6 tensions. Yeah, all will have same acceleration. You'll get 6 equations and solve. It can be done. It goes lengthy. But if you use the net force method, it is one equation. Step 1, assume any direction. Is it going left or right? You decide. Doesn't matter. Science will take care of it. When numbers are actually given, the sign will come out. Take right side for convenience. It looks like it will go right. So finish it off. Yeah, if you don't know this net force method, and this thing will look like a monster. But if you know your net force method, it's actually doable. Without writing an equation, you can see and tell the answer. I know answer is too big to type. Don't worry about it. I'll give a minute more and I'll show you. Let's see. So I will assume you are going this way. So what is M6 doing? M6 is supporting you, M6G. M5 will go this way then. What is M5 doing? M5 is also supporting, but with what? Not full force. M5G sine beta. M4 is going this way. What is M4 doing? Nothing. M3 is going this way. It is supporting M3G sine alpha. M2 is doing nothing. M1 is even more hopeless. It is actually opposing. You're done. So acceleration, all the guys who are supporting M6G, M5G sine beta. So these are all the forces along the string. That is the word, along the string. M3G sine alpha and M1G by total mass. Even though you don't support, you will participate in the net force. It's like your friend who comes to the party, doesn't bring anything but will eat all the food. There. No equations, nothing you got an answer. How do you find the tension? That is even cool. What did I say? If you want to find tension, what should you do? Cut it. Wherever you want to find tension, cut it. So you want to find tension here, so cut it. I'll just remove all this and I'll take till here. Then this point will have a tension T. So the right side system will think this is the only force which is pulling. Now apply the same story. What is the net acceleration? Acceleration will be net force. How much is that? M6G is supporting. M5G sine beta is supporting. And what is the tension doing? It is opposing by total mass, which is M5 plus M6. There you got your tension. Is that making sense? If you ask this system, what is happening on this side? It will say someone is pulling me with T, right? M5, M6 does not know who is 1, 2, 3, 4. Is that making sense? You want tension in the middle? Just cut it there. You'll get two parts. Take any one part and draw the FBD. Same story. So that you know the value of A from here, you can substitute, you will get it. It's lengthy, but that's how you do it. All clear with this? Any doubts on this? Then that's a bit about police. So with that, we'll wrap up for the day. Next class, when we catch up, Wednesday, we'll continue from here. We'll do more varieties there. We'll bring more pulleys and more things. We'll keep moving. So that is there. And then maybe we'll do a little introduction of springs also. We should be able to finish other chapter in another 2.5 classes. Then we'll start off with friction. The main thing was FBDs and constraints. If those two were comfortable, what is the extra thing, right? Writing equations and solving, isn't it? So there are only 4 steps. Draw FBD, write constraints, write equations, and solve. So we spent a good amount of time on the first 2 steps. So the remaining 2, that's the reason questions were going on. But that is the idea there. ठीक है, with that we'll wrap up for the day. I'll see you guys again on Wednesday. We'll continue from here. So, but I think NLM you can start doing with whatever I taught you till now. You will be able to handle most of the questions. HCV तो आराम से हो जाएगा. So you can start doing, but after next class you can do even much more. ठीक है, with that we'll wrap up for the day. So I'll see you on Wednesday same time. So any doubts, anything else, please stay back.